Good afternoon. We are going to continue with transients. We had discussed RL circuit transients in the last class. So let me first of all recall that as to whatever we had done in the last class. So in RL circuit transients, we discussed two types of circuits. One is with an exciting source, which is a DC source, and we had R and L connected like this. And we had actually a switch here, which we had a switch here, which was closed at time t equal to 0. So this switch was closed at time t equal to 0, and this is the R and L that we had talked about. Okay, and this is VDC. So in which case we said that Ri plus L di by dt equal to VDC. This is the governing equation. This is the first order differential equation. That is the reason why we call generally these kinds of RL circuit or RC circuit as first order circuit. On the other hand, if we are going to have L and C, both of them included in the circuit, we will have a second order equation. We will have a term which will be d square I by dt square, or d square v by dt square. So in that case, we would say that particular system is a second order system or second order circuit. So this happens when both L and C are included in the circuit. Okay, we'll be studying about this a little later after completing the first order systems fully. So in this particular case where R and L are connected in series with the voltage source, we derived the expression for I of t. So I of t we derived as VDC divided by R, which is the steady state current, and it is added to VDC divided by R multiplied by e power minus t by tau. Actually, VDC multiplied by R, VDC by R multiplied to minus e power minus t by tau. So where we called tau as the time constant. So the time constant is consisting of the expression which is L by R. So the steady state current what we are talking about, that depends upon what is the value of VDC and what is the value of R, and it doesn't depend upon L at all, because at time t equal to infinity, we said that L is going to act like a short circuit. When there is no rate of change of current at all, there is not going to be any voltage drop across the inductance. So the entire voltage will go towards pumping the current through the resistance in steady state. So we wrote this as two portions. One is the steady state response, and the second one is the transient response. And transient response completely depends upon what is the value of L and R, the inherent circuit parameters. So we are going to have this as, we call generally the transient response as natural response of the circuit. We call that as the natural response of the circuit because this mainly depends upon the circuit parameters and also the initial condition. And this is generally known as the forced response because this is essentially stimulated or activated by the excitation. The excitation in this particular case is the DC voltage. We are exciting the circuit with the help of a DC voltage. So this particular thing is called forced response and the other one is called natural response. Just to make this clearer, what is really natural response and what is forced response? Let us assume probably there is a frame to which you are attaching a spring. And if this particular spring is kind of twanged or pulled by you, and then you leave it, it will go through oscillations. If we are not holding it in a particular position, this will go through oscillations and finally it will settle down in its equilibrium position. So this oscillation, what it is going through, that is essentially the natural response, because you are not having any forcing function at all on this spring. And you are allowing it to settle down finally at its equilibrium position. So this is basically the steady state condition, what it is settling to. And the oscillations that are going, that the spring is going through for a short while, that is called transient response or natural response. It depends upon what is the kind of spring constant the spring is having, and what is the kind of initial condition the spring was having, and if there is some kind of friction associated with this or damping associated with this, right? Those things are going to play a vital role in deciding how many oscillations or how much is the amplitude of oscillation the spring will go through. So these oscillations, which are supposed to be the transient condition, it completely depends upon the inherent parameters of the spring itself. On the other hand, if let us say I have a spring balance, which is attached to your weight. So maybe the weight is hanging at the end of one end of the spring. So in this particular case, how much this spring is really elongated, that is depending upon how much is the gravity pulling this weight. How much is the kind of force the gravity is exerting on this particular spring. So the kind of elongation you see finally, that is the force response of the spring. The forcing function in this particular case would be the weight, what or the mass which is hanging from the spring balance. Okay, whereas before it reaches really the elongated position, it would have gone through several oscillations. Those things are dependent upon very clearly whatever is the natural response of the system or the transient response of the system, which are dependent upon the inherent parameters of the spring itself and the initial condition as well. So whenever we talk about the response of any system, whether it is a circuit, whether it is a mechanical system, whether it is any kind of pneumatic system or any kind of system, we are going to get a total response from the system, which will consist of two portions. One is going to be the forced response, which can be dictated by what kind of force or external excitation that I am applying. And the other one is going to be dictated by the parameters of the system under consideration. So these two are going to make up for the total response of any system. Now coming back to the RL circuit response, we said that when we have an RL circuit excited by a DC source, we said that I of t is given by VDC divided by R minus VDC divided by R multiplied by e power minus t by tau, where tau is equal to the time constant, which is L by R. So how quickly this current reaches steady state, that is dependent upon what are the relative values of L and R respectively. That is going to decide how quickly the system would settle down to its steady state value. So just to draw this graphically, we can say if this is I of t and this is the time, the current is going to start from 0 and then it is going to reach the steady state somewhat like this. So if I am looking at What is the steady state value of current? That is VDC divided by R. Okay, so I'm going to have I of 0 equal to 0 because initial current is not there. The current is slowly building up. So I'm going to have this as R, and this is going to be L, and this is going to be VDC. So I am essentially looking at initially the current is 0. Because the current is 0, so this is going to be 0 at t equal to 0 when time is 0. So because of that, if I try to look at Ri is also going to be 0 when I talk about at time t equal to 0. So when I write the Kirchhoff's voltage law, I wrote this as VDC equal to Ri plus L di by dt. And initial condition is Ri is going to be equal to 0. So if this is 0, the entire voltage has to come across the inductance. So I should be able to write this as di by dt equal to VDC divided by L at t equal to 0. When time t is 0, I'm going to have this as the di by dt value. And I know that the steady state current is VDC divided by R. So if the initial rate of rise of current, which is di by dt at time t equal to 0, if it had been retained at the same value. So that's what we said when we defined the time constant. So if I am going to retain the initial di by dt at the same value, so this is what the di by dt, this line, the slope of this line is indicating the initial di by dt. So if I had maintained the same di by dt value, then how long would it have taken to achieve this steady state current? So I can calculate time taken to reach ISS if initial di by dt is maintained. So that has to be essentially ISS divided by di by dt. That should give me the time. So I can say that is VDC divided by R, and the initial di by dt is VDC by L. So I should be able to write this as multiplied by L by VDC. So now these two get cancelled. So what I get is L by R. So the time constant is that time duration in which the current would have reached the normal steady state value provided the initial di by dt had been maintained. So this is graphically the time constant what we get within which duration you are going to have the full value of current reached provided the initial rate of rise is maintained. Now, in actuality, how much is the current value at time equal to time constant? So what I'm trying to say is at t equal to tau, what is I of t in reality? That's what we are trying to find out. So we said that this is the function for I of t. So I of t is VDC divided by R multiplied by 1 minus e power minus t by tau. Now, we said that t is going to be equal to tau now because we want to find out the current value at t equal to tau. So I of t equal to tau is VDC divided by R multiplied by 1 minus e power minus tau by tau. So that is e power minus 1. And we calculated this to be approximately 63% of VDC by R, or this is 0.63 VDC by R. So when the current is ultimately in time t equal to infinity, if it is reaching VDC by R, at time t equal to tau, the current is going to be reaching the value of 0.63 multiplied by VDC by R. So this is what is the time constant of the system. And in the same case, we should be able to calculate what is the kind of voltage across the inductance, how that is changing. We wrote this as the equation for the transient, and we know that L di by dt is going to be the voltage across the inductance. So I should be able to write this as L multiplied by VDC by R. Okay. And I have to say, when I differentiate this, this is 0. So I should just write minus of e power minus t by tau. That has to be differentiated with respect to time. So this is going to be the value of VL. So this will be VDC divided by tau, because R by L, right? So L by R, so I should say VDC multiplied by tau. This is VDC multiplied by tau. L by R is tau. So I'm going to have tau multiplied by VDC. And when I am differentiating this, I should have minus into minus plus. So 1 by tau multiplied by e power minus t by tau. So I'm going to have essentially this tau and this other tau will get cancelled. So I should be able to write this as VDC multiplied by e power minus t by tau. This is the equation or function for VL of t with respect to time. So if I try to plot the inductance voltage, for example, if I try to plot the inductance voltage, let me write this as VL of t. It is going to start from VDC and then it is going to fall down to 0 eventually. At time t equal to infinity, this will be e power minus infinity, because of which I'm going to have 0. So at time t equal to infinity, VL is going to be 0. Okay. So this is going to be 0 when I'm talking about time t equal to infinity. So again, I should be able to apply a similar, time constant and all that. So when I talk about time constant in this particular case, if it retains the initial rate of change of voltage here also, it would have reached 0 within a period of time constant. So if I try to look at what is the kind of voltage it would have retained compared to the initial value at this point. So if I try to look at what is the amount of voltage it has retained at time t equal to time constant, that will be 1 minus 0.63. So this will be approximately 0.37 times initial voltage. If I may call this as VL initial, this voltage as VL initial. So compared to VL initial, this will be 37% of the original or initial voltage. So we also looked at one more circuit where we just took R and L, where L was having an initial current. So the L was having an initial current, let us say in this direction. So this is going to have a stored energy which is going to circulate the current through R because of the stored energy until it is completely dissipated in the resistance itself. So this is really the natural response of RL circuit with some initial current in the inductance. Okay. So in this particular case, we said that if the initial current is I naught, let's say. So we are going to have I naught multiplied by e power minus t by tau as the response of this particular I. If I may call this as I of t is going to be like this. So this is going to essentially give me an exponentially decaying function where tau is L by R. So this is what we discussed in the last class. So we talked about basically RL circuit with an exciting function and RL circuit without any excitation, only with an initial value of inductive current, where the natural response is manifested by the R and L circuit in the form of transients. Now that we have understood what is natural response, what is forced response, and how RL circuit behaves, what is time constant, and so on. Let us now go on to understand the second kind of transient response with another element called RC circuit. So first of all, for this, we need to understand what is a capacitor. A capacitor is basically two plates, two metallic plates, which are segregated or separated from each other with the help of an intervening dielectric or insulator. So I'm going to have an insulator in between these two. So I'm going to have both these things, this as well as this, as metallic plates. And this is going to be insulator or dielectric. Now, this is what is a capacitor. And if I look at the capacitor being connected to, let us say, a DC source like this. So let us say I have connected this to a DC source. And this is having a potential difference of VDC. So this battery is having a potential or voltage that is available as VDC. Now, when I connect this to a capacitor like this is at zero potential. This is not charged at all. So now what is going to happen is the electrons from this metallic plate that is going to run towards the positive plate of the battery. So this is going to be depleted of electrons, whereas this is going to get rich in electrons. So the electrons are going to move towards the negative plate of the capacitor. The tendency of electron is always to be forced by any positive charge, positive potential difference that is available. So potential difference or voltage is also generally termed as electromotive force, EMF, electromotive force, because this is essentially acting like a force which is making the electrons move. The electrons always move towards the positive plate, and the electrons always move away from the negative plate. So you're going to have depletion of electrons in this particular plate and accumulation of electron in this particular plate. So we can say that if I call this particular plate as plate A and this as plate B, plate A becomes positively charged with respect to B, plate B. So we will have a potential difference existing between these two. And when this potential difference becomes same as that of VDC, then there will be no more current. So the current is flowing in this direction, whereas electrons are flowing in the opposite direction. So the current will flow until the potential difference achieved by this capacitor is equal to that of the potential of the battery or voltage of the battery. Okay. And this energy stored in the capacitor, we call that as electrostatic energy. Whereas what we see in an inductance. In a capacitor, it is electrostatic energy, whereas in an inductor or inductance, it is called electromagnetic energy. So in an inductance, if you disconnect the inductance from a circuit, you are not going to be able to make the inductance retain its energy, because once the current is gone, once you disconnect the inductor, there cannot be any current anymore. Current cannot flow in an open circuit. So the electromagnetic energy cannot be retained by an inductor which is disconnected from a circuit. But in a capacitor, it can retain the charge definitely for longer duration. So electrostatic energy can be retained by a capacitor, whereas electromagnetic energy cannot be retained by an inductor the moment it is disconnected from the circuit. So this is one of the major differences between a capacitor and an inductor. Another thing is that if we say that this particular capacitor, if we say that this particular capacitor is getting a potential difference of V, and if it is having a charge accumulated between the two plates as Q, now Q is generally written as CV, where C is the capacitance in farad. So the capacitance is defined as the ratio of the charge accumulated to the potential difference between the two plates of the capacitor itself. So this is how the capacitance is defined. Now if I say Q divided by V is equal to the capacitor value, capacitance value in farad. So I should be able to write this as Q I can write as I times T. Okay. And I can write I times C, T equal to C times V. So if I pass a current of I for a duration of delta T, for a short duration of delta T, then there will be a slight increase in the voltage of the capacitor, which is delta V. So I should be able to write this as I equal to C times dV by dt. So this is the expression corresponding to capacitor current when I relate it with the voltage. Please remember, in the case of resistance, it was I equal to V divided by R. It is in direct proportion to the voltage. Whereas here, the current depends upon the rate of change in the voltage. The same way, if I try to look at the inductance, its voltage depends upon the rate of change in the current. Right? So the capacitance and inductance, they have similar behavior, but only thing is the VI relationship is somewhat inverted, where I have C dV by dt equal to I, whereas V is going to be equal to L di by dt. That is the way you are going to have the voltage and current relationship in the case of inductance and capacitance. So that's the reason why normally we say capacitor and inductor are dual of each other, because both of them in one sense have similar kind of relationships, but inverse relationship if we consider V and I simultaneous. Okay. One more thing we can say is, if I talk about energy stored in an inductance, and similarly energy stored in a capacitor. So we said that V equal to L di by dt. That is what is the expression for inductance relationship between the voltage and current. So I can say the power, instantaneous power. If I try to calculate, that should be V multiplied by I. I'm writing instantaneous power. Instantaneous power is V multiplied by I. So I should be able to write this as L di by dt multiplied by I. Okay. Now if I want energy stored in the inductance within a duration dt, then I should write this as I multiplied by L di by dt multiplied by dt. So this dt and this dt I can cancel. So I'm going to have I L di. This is going to be the energy stored within the duration of dt. Now, if I want the complete, for the complete duration of t, within which the current is going to increase from 0 to some capital I. Let us say the current is increasing from some 0 value to some capital I, and I want to know how much is the energy stored in this duration. This will essentially come out to be I square by 2 multiplied by L. So this is essentially half L I square. So this is the energy stored in the inductance, electromagnetic energy stored in an inductance when a current is slowly building up from 0 value to some particular value I. So this is the total energy stored in an inductance. Whereas if I try to calculate the same kind of energy stored in a capacitor, I should say again instantaneous power P in a capacitor. That is going to be equal to V times I. And we wrote already C dV by dt as I. This has to be multiplied by V. So this is going to be the instantaneous power. So if I want energy stored in the capacitor, I should say that is, integral of 0 to certain V value, which has to be actually V multiplied by C multiplied by dV by dt, and this has to be integrated with respect to time. So in this particular case also, this dt and this dt will get cancelled. So I should be able to write this as half C V square, where the maximum voltage reached by the capacitance is V. Whatever it has accumulated as charge, and that is manifesting in the form of a potential difference, which is V. So half CV square happens to be the energy stored by a capacitor, and half Li square happens to be the energy stored by an inductance. Okay, so both of them have very similar expressions. Only thing is, wherever the voltage is utilized in the case of capacitor, the current is utilized in the case of an inductor. Okay, now let us quickly try to take a look at what happens when you connect capacitors in series and parallel. So capacitors in series and parallel. So let us try to quickly take a look at this. I'm sure all of you know how we calculate the series and parallel combinations of resistances. What is the equivalent that is visualized by the circuit? So for example, if I'm going to have a voltage source Vs is connected here. This is R1, this is R2. Both of them are in series. So I'm going to have V1 across this and V2 across this. And I'm going to have a current which is I flowing through this. When both resistors are in series, the same current flows through both of them. So I should be able to say Vs equal to IR1 plus IR2 or V1 plus V2. which should be equal to whatever is the current that is seen from the source side, which is I, multiplied by R equivalent. That's why we say R equivalent when two resistors R1 and R2 are connected in series is R1 plus R2. So R equivalent is going to be equal to R1 plus R2. Okay. On the other hand, if I'm going to have this are the two resistances R1 and R2 and they are connected in parallel, and I'm going to have this as the voltage source which is connected here. So I'm going to have the voltage across each of these resistances to be Vs. Okay. And the total current here is going to be I. And this is I1 and this is going to be I2. So I have to write I is equal to I1 plus I2. And this I should be whatever is the resistance that is seen from this terminal of the source, these two terminals of the source. So this will be V divided by R equivalent that is seen across the terminals of the source. That will be equal to V divided by, rather Vs, the source voltage, Vs divided by R1 plus Vs divided by R2, from which we say 1 by R equivalent in parallel connection is 1 by R1 plus 1 by R2. So this is what is the expression that we get for series and parallel connections of resistors. Inductances follow exactly the same rule, exactly similar rule as compared to resistor. Okay, they behave exactly the same way when you connect them in series or parallel. Let us try to take a look at what happens when two capacitances are connected in series. So when two capacitances are connected in series, let me draw the circuit again. So I'm going to have this as the voltage source. Maybe this is V, and one capacitor is connected here, another capacitor is connected here. Okay. A common current I flows through this particular capacitors connected in series. So I times T, whatever is the time duration for which the current is flowing, that is going to be the Q, total charge accumulated by both the capacitances. Okay, let me call this as C1 and this as C2. These are the two capacitances that we are talking about. Okay, now we know that whatever is the voltage across this and voltage across this, when you sum them up, you are going to get this total voltage V. So V is going to be equal to V1 plus V2. Okay, and you can say the total amount of charge supplied divided by whatever is the equivalent capacitance that is seen by the source itself. That is going to be equal to whatever is the charge that is accumulated divided by C1 and whatever is the charge accumulated totally divided by C2. So this relationship has to hold good because the total amount of charge that is transported is the current which is common to both the capacitors multiplied by the time. So from here I should be able to say the equivalent capacitance when two capacitances are connected in series is equal to 1 by C equivalent equal to 1 by C1 plus 1 by C2. Whereas when I have two capacitors connected in parallel, when I have two capacitors connected in parallel, I'm going to have basically the circuit somewhat like this. So I'm going to have the source voltage here, which I'm calling as V, and I'm going to have one capacitor connected across like this. Okay, so let me probably redraw this properly. So I'm going to have one voltage source here and one capacitor connected in parallel like this, and one more capacitor again connected in parallel like this. Okay, now I'm going to have this as C1 and this as C2, and this is the voltage V, and I'm going to have I1 flowing through this and I2 flowing through this. So Q1 is going to be the accumulated charge here, and Q2 is going to be the accumulated charge here. Now the voltage is going to be common across all the branches because all of them are connected in series, parallel. So I'm going to have V equal to Q2 divided by C2. That is also going to be equal to Q1 divided by C1. Okay. And this should be whatever is the total charge that has been transported, the total Q divided by whatever is the C equivalent. So this is what is going to be the overall expression for voltage when I write it. Okay. Now, because I am saying that Q equal to Q total equal to Q1 plus Q2 multiplied by divided by C equivalent. Okay, so I should say this is Q total is going to be equal to, sorry, this is Q1 plus Q2, which is C equivalent multiplied by voltage. So I should say Q total equal to C equivalent multiplied by voltage, which should be C1 multiplied by V, C1 multiplied by V, and C2 multiplied by V. Right? So from this, I should be able to say the C equivalent as seen from the source terminal has to be equal to C1 plus C2 when two capacitors are connected in parallel. So again, please notice that the capacitance behaves exactly in the inverse way as compared to an inductance, because in inductance, when two inductances are connected in parallel, you will have L1 parallel L2 will be 1 by L1 plus 1 by L2 equal to 1 by L equivalent. Whereas here it is C equivalent equal to C1 plus C2. So I want you to kind of notice the difference in the behavior of inductance and capacitances. Okay. Now let us try to look at RC circuit transient. So let us try to take a circuit somewhat like this. This is the VDC that I'm connecting, and I have a switch, and I'm going to have a resistance and a capacitance here. Okay. Now I'm going to close the switch at time t equal to 0. The switch is going to be closed at time t equal to 0. So we'll have to write the KVL equation for this. So KVL equation is going to be VDC equal to RI plus whatever is the voltage across the capacitor. So we already said C dV by dt equal to I. So I can say whatever is the voltage across the capacitor is going to be I dt integrated, and which has to be divided by C. So I have to write this as 1 by C integral ID. This is going to be the differential equation corresponding to this RC circuit. Assuming that there is no charge in the capacitor initially. If there is an initial charge in the capacitor, I should write this as Vc of 0. That also has to be added depending upon what is the direction of current that I am taking. So if I take that this is going to be the direction of current, the capacitor voltage is actually going to oppose the flow of current, or the voltage is going to increase as the current flows further and further. So I could have taken the sign as positive. That's not a problem. Now in this particular case, we are going to assume that Vc of 0 is 0. So initial voltage across capacitor equal to 0. So if I call this as equation number 1, I can differentiate this equation number 1 to get a differential equation. So differentiating 1 with respect to time. I'm going to get dVdc by dt is 0 because it is a constant voltage source. So it is going to be 0 equal to R di by dt plus I divided by C. So I can rewrite this equation somewhat like this. I can say di divided by I can take the minus sign on the other side, and I can say dt divided by RC. So to solve for the current, I can integrate on both the sides. So I can integrate here as well as integrate here. So when I integrate on both sides, here I'm going to get minus ln of I. This is what I'm going to get. That is equal to T divided by RC. Of course, I have to have a constant here, some K naught. A constant has to be there. So this is the constant of integration. This is going to be the constant of integration. So K naught can be solved for by substituting the initial condition. Now, please remember what we are talking about is the initial condition for the current, because we have solved for the current. So the initial condition for the current, if we want to look at, this is at 0 voltage. There is no voltage at all. Whereas this is having a voltage of plus VDC. So if I look at the voltage at this point, this is 0. Whereas if I look at the voltage at this point, it is VDC. So the current that is flowing initially is going to be VDC by R, because that is essentially the potential difference which is coming across this resistance. So I of 0 is going to be equal to VDC by R. So I can say when time t equal to 0, I of 0 is equal to VDC divided by R, or I of t is going to be equal to VDC by R. So I can substitute that in this equation. So by substituting that, what I can say is K naught minus ln of VDC divided by R is equal to T by RC. T is 0 divided by RC. So that is going to be equal to 0. So I can say simply K naught equal to ln of VDC by R. So now I can substitute this value into the original solution what I have derived. So I can say K naught is ln of VDC by R minus ln of I equal to T by RC. Because these are logarithms, I should be able to write this as ln of VDC by R divided by I. Natural logarithm of this equal to T by RC. If I actually inverse this, I should be able to write this as ln of I divided by VDC by R equal to minus T by RC, from which I should be able to write this as e power minus T by RC equal to I by VDC divided by R. So I can say VDC divided by R multiplied by e power minus T by RC equal to I or I of T. So this is going to be the current expression, which is quite obvious because if you look at the circuit condition, this current is flowing this way and it is starting with a very high value, which is VDC by R. And as the capacitance accumulates charge, this potential is going to increase from zero. It is going to become higher and higher. So obviously I has to come down. The current will come down automatically as more and more time is elapsed. Okay. So this is the way this RC circuit is going to behave. So if I try to draw the current will start from VDC by R and it will decay exponentially, and this is time, and this is going to be I of t. Okay, so it will take as long as R and C values are determined by R and C values. If R and C both are high, this is going to take really a long duration to reach zero value. So this is the way the current response is going to be. Again, extending the same way like what we had done in our original RL circuit, if the initial rate of decay had been maintained at the same value, then definitely I'm going to, so if you look at this, initial rate of decay, you should be able to calculate based on di by dt. So if you calculate, then you would be able to find the initial di by dt, and using that, you should be able to say from VDC by R to reach zero value, how long it would take if the initial rate of decay had been maintained. So if the initial rate of decay had been maintained, at what time the current would have reached zero, this is the time constant. And if I look at what is the actual value of current at this particular time constant, it will turn out to be 37%. That is I of t equal to tau. If I want to calculate, in this particular case, of course, tau is going to be RC because e power minus t by tau, that's what we are writing as the rate of decay with respect to, the initial current value. So this is going to be the current value. So this T has to be now replaced by minus tau and divided by tau. So this is going to be VDC divided by R into e power minus 1. And this happens to be 37% of VDC by R. So time constant in RC circuit is given by R, the product of R and C. And within that time duration, the current is going to reach 37% of its original or initial value. So this is going to be the trajectory of current. Now, if I want, what is the voltage across the capacitor? We already wrote the expression as 1 by C integral I dt. So this is 1 by C integral of VDC divided by R into e power minus t by tau of dt. This is going to be the expression for Vc of t. So in that case, I should be able to write this as Vdc by Rc multiplied by, this is minus 1 by tau. Right? And I'm going to have e power minus t divided by tau. So this is going to be the voltage expression with respect to time. Now RC is tau. So this is going to be integral, right? So it cannot be 1 by tau. It has to be minus tau. Sorry, this has to be minus tau. So this tau and this RC will get cancelled with each other. So I'm going to have VDC multiplied by e power minus t by tau plus whatever is the initial voltage value. Okay. So this is going to be solved for by substituting the initial condition. So I should say VC of 0 equal to 0. That's what we had assumed. Initial value of capacitance voltage is 0. This is at time t equal to 0. So this is going to be VDC multiplied by, so this is going to be VDC plus K naught. Right? So I'm going to have, this is minus sign I have missed out here. So this is minus, so minus VDC plus K naught equal to 0. So K naught is going to be VDC itself. So this is the integration constant. It's not even initial voltage value. This is integration, constant of integration. So the constant of integration comes out to be VDC. So now I can write Vc of t is equal to, right? Minus VDC multiplied by e power minus t by tau plus VDC. So this happens to be VDC multiplied by 1 minus e power minus t by tau. So if I draw the voltage curve for the capacitance, so this is Vc. So this is time. So I'm going to have essentially the voltage rising from 0 and reaching the maximum value like this. So this maximum value will be VDC itself, whatever is the source voltage that I'm connecting across the RC series connected components. Okay. So rather than this, if I try to look at the capacitance is already charged. Let me look at the circuit somewhat like this. Maybe I'm going to have one switch here and I'm having an R and the capacitance is getting charged here. Okay. And I'm going to have one more switch here which is connected to a small R. So let us say this is S1 and this is S2. So at time before 0, this was closed. So this is when t was less than 0. Now this switch S1 is going to be opened at t equal to 0 and S2 is closed. So S2 is closed at time t equal to 0. So now I'm going to have the capacitance having plus here and minus here. The moment this resistance is connected, this capacitance is not going to keep quiet. It will try to discharge a current in this particular direction. So this is going to be I dash. So if I try to derive an expression for I dash, so let me try to draw the circuit once again. This is R and this is going to be the capacitance, and this is plus, and you're closing this switch. This is small r. So I'm going to have a current like this, which is I dash. Okay. Now I have to write this equation again. This is initial voltage. Let me call as VC initial, whatever is the initial voltage. So I'm going to write this as R I dash plus 1 by C integral I dash dt and plus whatever is the initial voltage, that is going to be equal to 0. Whether this is plus or minus, we have to think. As the current is increasing, the current flows further and further, this voltage is going to decrease. So in all probability, I have to have this as minus. It should not be plus, because as the current flows, whether this voltage is increasing or decreasing, that's what I am trying to look at. The voltage is decreasing, so it is minus VC initial. So I can write this as R I dash plus 1 by C integral I dash t equal to VC initial. If I may call this equation as the system equation, which is describing the function of the system, that is extremely similar to what originally we had written here. Both of them are exactly one and the same. There is hardly any difference between these two. So if I differentiate this equation, let me call this equation as 2. So differentiating 2, we are going to get R di dash by dt plus I dash divided by C equal to 0. So the solutions are exactly going to be similar. So I will have I dash of t equal to whatever is the initial current, which is going to be VC initial divided by R multiplied by e power minus t by tau, where tau is going to be small r times C. So the solution what we get for the natural response as well as the forced response, they look exactly similar in the case of an RC circuit. Okay. So to compare RL circuit and RC circuit with excitation, I'm trying to compare the two with excitation. Okay. So if I say what is the time constant? Tau. So that is going to be L by R, whereas here it is going to be RC. Okay. And I'm going to have the current. If I try to look at what is the current, I'm going to have in one case VDC divided by R multiplied by 1 minus e power minus t by tau. Whereas here it is going to be VDC divided by R multiplied by e power minus t by tau. So it decays completely to 0 at the end of the entire circuit reaching steady state. On the other hand, if I'm going to look at either VL of t or VC of t, I'm going to have in this particular case, VL of t is going to be whatever is VDC initially multiplied by e power minus t by tau. Whereas here it is going to be VDC multiplied by 1 minus e power minus t by tau. Okay, so please note that RL circuit and RC circuit behave exactly in the reverse way. That is, whatever is the expression for current I got in the case of RL circuit, almost similar expression I'm getting for voltage in the case of RC circuit. Similarly, whatever I got as the expression for current in RC circuit, RL circuit, voltage of across the inductance in an RL circuit, and the current through the capacitance in an RC circuit, they look exactly similar to each other. Okay, so both RC circuit and RL circuit are called as first order systems because they are described by first order differential equation. We'll be working out a few problems in the next class based on these first order